Okay, so we just got finished talking about the area under a curve. And when we talked about the area under the curve, it was between the curve and the x-axis. Okay? Okay, so this is what we did, right? We broke it up into all these little triangles, okay, that were infinitely small, and we summed up these infinitely small rectangles, okay? That was basically our derivative, where this was the height and the width, right? Okay, so if you were to guess how to find the area between two curves, does anybody have maybe a little bit of an idea? All right, Tanner said take the bigger one and then subtract the smaller one. How do you feel about that? It sounds pretty reasonable, right? Right, right. Well, we would want the taller rectangles minus the shorter rectangle, right? Okay. So this is how it's going to work. In order to find the area between two curves, we are going to subtract our lower curve from our upper curve, okay? Because what's happening, we are going to take these rectangles from this upper curve, right? There's infinitely many. And then these are the rectangles for the lower curve. And if we subtract them, we have the rectangles that are inside that blue area. Okay, so typically what I do, all right, because our limits of integration are going to be the same, I typically combine them. So the integral from a to b of our top function minus our bottom function. Okay, that way you only have to plug in the limits of integration once. Is anybody worried about if our curve is underneath the x-axis? Is this still going to be okay in those situations?
Yeah.
Okay, because it's going to be minus those negative rectangles, and so they really be added. Okay? So this is going to work no matter what. No matter what. Top minus bottom. Bigger rectangles minus smaller. Okay? We're subtracting the lower from the upper. So upper minus lower. Okay. Okay, so I want the area of the region bounded by y equals x plus 6, y equals x squared, x equals 0, and x equals 2. What do you think the first thing I'm going to require you to do? We need a hook. Okay, we don't need a calculator for this one. We don't need a calculator. All right. Y equals x squared. What is it? I said y equals x squared. Okay? Y equals x plus 6.
Fine.
Right? We have y-intercept of 6, slope of 1. Okay? And then we want between x equals 0 and x equals 2. So here is x equals 0 and x equals 2. So the region enclosed by these 4 curves is this. Okay. Now the nice thing about this problem is they basically just gave us the limits of integration, didn't they? They want between 0 and 2. Okay? Well, we're going to integrate. Okay, we're basically taking these infinitely small rectangles with thickness dx, with width dx, from 0 to 2. Okay, so let's set up our integral. What is our top function? It's the line, right? So our line x plus 6 minus our lower function x squared. Our rectangles have thickness, have width dx. This is their height. This is their width. All right. This is nice, isn't it? Integral of x plus integral of 6 minus integral of x squared. We're going to integrate this from, or we're going to evaluate this from 0 to 2. All right, we plug in 2. 1/2 2 squared plus 6 times 2 minus 1/3 times 8 minus, when I plug x into all of those, it's 0, right? I plug 0 into all of them. I am sorry, baby. Okay, what is 2 plus 12 minus 8/3?
11/3. Or 11.3. 34/3.
Okay. There might be a couple of problems like that. Okay. Now, this one was nice because they basically gave us our limits of integration. Most times we're going to have to determine what the limits of integration are. Okay. We have a parabola and a line, 2 very easy things for us to graph, and 2 very easy functions for us to integrate. Agree? So let's see, y equals 2x. Line. I like graphing the lines first, or I don't know.
Yeah.
I know, I did. Okay, we'll go from left to right. Y equals x squared. Parabola, right? Okay. And then y equals 2x. Y-intercept of slope of okay. So we want the area enclosed by these 2 graphs. All right? Which means we're talking about this area right here. Now we were lucky and we're able to tell from our graph where these two intersect, okay? However, if you are not sure what could you do? What if we don't have our calculator?
Yes.
We want to know where they are equal. So when is x, oh my goodness, look at this equation, people. When is x squared equal to 2x?
Zero. 0 and 2.
Okay, x squared is equal to 2x at 0 and 2. When x is 0, y is 0. When x is 2, y is 4. Doesn't really matter about our y coordinates because we're adding up these vertical rectangles with thickness dx. Alright, so we are integrating from
0 to 2.
0 to 2 because that's where our curves intersect. Alright, our upper function.
2x.
Our upper function is 2x. It's above. Our lower function below is
X squared.
okay. We're doing this without a calculator right now. When we integrate 2x, we're going to evaluate this from 0 to 2. We have x squared. When you plug in 2, we get 4 minus 8/3. And then we're going to subtract. When we plug in 0, we get 0. So we have 12/3 minus 8/3. So our area is 4/3. Not red region. Okay. Any questions so far? Feeling okay about it? For the most part? For the moment. You don't know how to graph your questions? Okay, we have the region. Excuse me. We have the region enclosed by y equals x squared and y equals x minus 2. Okay, now first of all, what is x equals what to? A sideways parabola, and it's going to open which way? To the right. Okay, y equals x minus 2. The line. We have a y-intercept of -2, slope of 1. Now, we are integrating if we have these, or if we have these vertical rectangles, we are integrating with respect to x. Right? Now, x equals y squared. That's really not going to work to cut in our integral, is it? Well, part of it. This curve right here is y equals radical x. What is this curve right here? Okay. Very good. Now, we have another issue. Okay, well, let's talk about where these intersect. Okay? Okay, we intersect at 1, -1. What about up there? Are you sure it's 4, 2?
Yeah.
Okay. Let's check. If x is 4 and I plug in 2 for y, does that work? If x is 4 and I plug in 2 for y, does that work? Okay. If not, you have to solve algebraically. Right? Okay. There's another issue. Does anybody see it? The negative part's okay. Okay, wait. What do you mean? Like some of it's under the x-axis? Is that what you meant? Okay, it's okay if we have some under the x-axis, because we're just subtracting negative rectangles. Okay? We're not adding.
Is it if we integrate from -1 to 2 with the 1 to 4, when you're going to cut off that little foot from 2?
Okay, let's look right here. What's our top function? Okay. Our bottom function is different from here to here, isn't it? Okay? Our bottom function is not always that line, is it? Okay? So we're talking about this area right here, but we're going to have to split it into 2 chunks. Okay? Because to the left of this line I just drew, y equals negative square root of x is the lower function. So when we get past that, when we get past x equals 1, x minus 2 is our lower function. Okay? So we're going to have to separate this into 2 different integrals. Okay? We are going to have the integral from 0 to 1, all right, where our upper function is the square root of x minus our lower function is negative radical x. All right, and so that's going to be that green area. Then the remaining red area, we're going to have the integral from 1 to 4, where our upper function is the square root of x minus our lower function is now that line, x minus 2. Notice how I put that in parentheses because we're subtracting a quantity. Okay? Is everyone okay with what we just set up here? If your lower function changes, you have to break it up into multiple integrals. So, let's simplify these integrals a little bit. Square root of x minus negative square root of x. We have 2 x to the 1/2. I'm not integrating it. I'm just simplifying it. Okay, is everyone okay with what I wrote? And I changed it to an exponent so it's easier for us to integrate. Plus, from 1 to 4, this is x to the 1/2 minus x plus 2. Yes. Okay. So we have 2 times what? Okay. From 0 to 1. Okay. Plus 2/3 x to the 3/2 minus plus evaluated from 1 to 4. Okay. When I plug in 1, what do we get here? Minus. When I plug in 0, 0. Okay. Plus, let's evaluate this guy. When we plug in 4, 3 halves, what does that mean as a power? Square root and cube. So what's the square root of 4? Cube. That's 2/3. Minus 1/2 times 4 squared. Plus 2 times 4. Minus, when we plug in 1, 2/3 minus 1/2 plus 2. Now, we don't have a calculator, right? What I would do, let's combine our fractions with a denominator of 3 first, because maybe it'll be a nice number, maybe not, I don't know. What is 4/3 plus 16/3? Minus 2/3. 18/3. 6. Okay? Negative 8 plus 8? 0. Negative half plus 2? Oh, very nice. Positive half minus 2. Four and a half. 4. Okay. Let's try a little bit of work. Okay. Now, what we haven't done, okay, from ever since we've been integrating with respect to x with our vertical rectangle. What if we made horizontal rectangles? What tool? Okay. We can make these infinitely small horizontal rectangles where our thickness is dy. Okay? Which means we're now going to integrate with respect to y, and we're going to take our right function take right minus left. And take right function minus left function. Because we're still going to take the larger rectangles minus the smaller rectangles. Okay, it's the same principle. You want longer rectangles minus shorter rectangles. So right minus left. Because our rectangles would be drawn all the way to the y-axis this time instead of the x-axis. Okay? So the more positive your function is, that's the one that's going to come first. Right to left, top to bottom. So here again, I would do one integral to make our life easier. Now, in this case, since our thickness is dy, we're integrating with respect to y. So we're going to have y's in here. And our limits of integration are going to be our y values. So we're going from, in this case, C to B. Okay? Whatever the thickness of your rectangles are, that's telling you what variable you're integrating with respect to, which tells you what limit of integration you need. Okay? It always helps me to draw my rectangles to remind me. Okay? So, we are going to do the same example, but with horizontal rectangles. What should our answer be? 9.5. 4.5. Better have it, right? Okay, let me redraw my picture. So remind me of our points of intersection. This was 1, -1, right? And this was 4, 2. Okay. Now, we want our functions in terms of y. So instead of y equals x plus 2, what would we need to write it as? Okay, this is the function x equals y plus 2. Now this function we already have in terms of y. X equals y squared. Okay, so to define the area now, our limits of integration, we're talking about right to left, so our rectangles are horizontal with thickness dy. So our y values for our limits of integration are going to be what? -1, 2, 2. Our very right function is y plus 2 minus our very left function is y squared. This is easier because there's less computation. Less. Okay? So, antiderivative of what? Plus minus 1/3 y. Okay? So now, 1/2 times 2 squared plus 2 times 2 minus 1/3 times 2 cubed is 8/3 minus 1/2 times -1 squared plus 2 times -1 minus 1/3 -1 cubed plus 1/3. Okay? So we have 2 plus 4 is 6. -8/3 minus 1/3. And then we have a minus 1/2 plus 2. 6 minus 3 is 3. And plus 2 is 5. Minus 1/2. Yay! Same answer. Okay. So there will be times where it says do this with respect to x, do this with respect to y. There will be times where you get to decide which way is going to be easier. There will be some ways that it is fine either way. One's just going to be quicker than the other. There are going to be times where you do not want to solve your equation for x or y, and it's going to be easier to just keep it the way that it is. Okay? So, your homework. Page 418, 1 through 7, 9, 15 to 21 odd, 42 and 43.